We are going to consider additional examples on definite integrals. Okay, let us have the first example and evaluate the integral of cosine of x dx from the lower limit 0 to the upper limit pi over 2. Of course, the integral of cosine of x is sine of x. And we are going to evaluate this from the lower limit 0 to the upper limit pi over 2. And since the definite integral is the value of the indefinite integral at the upper limit minus the value of the indefinite integral at the lower limit, then this gives us sine of pi over 2, the value of sine of x at the upper limit pi over 2 minus sine of 0, which is the lower limit. Of course, sine of pi over 2 or sine of 90 degrees is 1 minus sine of 0 is 0. Hence, the definite integral of cosine of x dx from the lower limit 0 to the upper limit pi over 2 is 1. Okay, in the next example, we will consider evaluating the integral of secant square of x over 1 plus tangent of x times the differential of x to be evaluated from the lower limit 0 to the upper limit pi over 4. Of course, we need to evaluate first the definite integral of secant square of x dx over 1 plus tangent of x, which leads to logarithm since the numerator is the exact differential of the denominator. So here, we can consider letting u is equal to the denominator 1 plus tangent of x, okay, whose differential is secant square of x dx, which is, of course, the numerator. Hence, the integral will lead to the natural logarithm of the denominator 1 plus tangent of x. So we have natural logarithm of the absolute value of 1 plus tangent of x, and this must be evaluated from the lower limit 0 to the upper limit pi over 4. And this is equal to the value of the indefinite integral at the upper limit pi over 4, so that we will have natural logarithm of 1 plus tangent of pi over 4 minus the value of the indefinite integral at the lower limit 0, giving us natural logarithm of 1 plus tangent of 0, which is equal to natural logarithm of 1 plus tangent of pi over 4, or tangent of 45 degrees is 1, okay, minus the natural logarithm of 1, tangent of 0 is 0, so that we will have natural logarithm of the absolute value of 2 minus the natural logarithm of 1. Of course, the natural logarithm of 1 is equal to 0, so that we will have natural logarithm of 2. We can simply write natural logarithm of 2 even without the absolute value minus 0. Therefore, the definite integral of secant square of x dx divided by 1 plus tangent of x from the lower limit 0 to the upper limit pi over 4 is natural logarithm of 2. Okay, this time we will consider evaluating the integral of f of x dx from the lower limit 0 to the upper limit pi over, from the lower limit 0 to the upper limit 4, considering that f of x is the piecewise function, okay, 2x plus 1, if x is greater than or equal to 0, less than or equal to 1. And f of x is 4 minus x if x is greater than 1, less than or equal to 4. Now, to evaluate the integral of f of x dx from 0 to 4, we are going to consider the property of definite integral, that if we have the integral of f of x dx from a to b, we can express this as sum of integrals of f of x dx from a to c plus the integral of f of x dx from c to b. So applying this property, then the integral of f of x dx from 0 to 4 is equal to the integral from 0 to 1, the integral of f of x dx from 0 to 1, plus the integral of f of x dx from 1 to 4. Now, from 0 to 1, f of x is defined as 2x plus 1. And from 1 to 4, f of x is defined as 4 minus x. Hence, the integral is equal to 2x plus 1 from 0 to 1, okay, plus the integral of f of x, which is 4 minus x from 1 to 4. Okay, so we are going to evaluate the integral of f of x dx from 0 to 4 as the sum of the integrals from 0 to 1 plus 1 to 4. Okay, hence, this will give us, okay, evaluating the integral of 2x plus 1 dx gives us 2x squared over 2 plus x. The integral of dx is x, and this must be evaluated from the lower limit 0 to the upper limit 1, plus the integral of 4 minus x dx. Of course, the integral of 4 is 4 dx is 4x minus the integral of x dx, which is x squared over 2. Okay, and this is to be evaluated from the lower limit 1 to the upper limit 4. Now here, we can actually do cancellation, okay, which will give us x squared plus x to be evaluated from the lower limit 0 to the upper limit 1, then plus 4x minus x squared over 2 to be evaluated from the lower limit 1 to the upper limit 4. Okay, so considering this indefinite integral x squared plus x, okay, to be evaluated from the lower limit 0 to the upper limit 1, the value of the indefinite integral at the upper limit 1 is 1 raised to the second power plus 1, okay, minus the value of the indefinite integral at the lower limit 0. Okay, of course, this will give us 0 squared plus 0. Okay, then plus the value of the indefinite integral 4x minus x squared over 2 at the upper limit. So at the upper limit, we will have 4 times 4 minus 4 raised to the second power divided by 2 minus the value of the indefinite integral at the lower limit 1. So that gives us 4 times 1 minus 1 raised to the second power over 2. So simplifying will give us 1 plus 1 is 2. Of course, this is 0. So that will simply give us 2 plus, 4 times 4 is 16. Okay, 16 minus 4 squared is 16 divided by 2. So that will give us 16 minus 8 minus 4 times 1 is 4 minus 1 half. Okay, and simplifying further will give us 2. Okay, this is 8. So if we will remove the parentheses, or the grouping symbol rather, that will simply give us 8 minus 4 minus 1 half is 7 over 2. Okay, which is equal to 10 minus 7 over 2. And 10 minus 7 over 2 is 13 over 2. Okay, hence, the integral of f of x dx from the lower limit 0 to the upper limit 4, if we are given the piecewise function, okay, f of x is 2x plus 1, when x is greater than or equal to 0, less than or equal to 1, okay, and f of x is 4 minus x, when x is greater than 1 but less than or equal to 4, is 13 over 2. Okay, this time, we are going to consider evaluating the definite integral of an absolute value of a number, say x. So let us consider evaluating the integral of the absolute value of x dx from the lower limit -2 to the upper limit 4. Okay, before we evaluate the integral of the absolute value of x dx, of course, we are going to consider the definition of the absolute value of the number x. Okay, recall that the absolute value of x is defined as x if x is greater than or equal to 0 and negative x if x is less than 0. Okay, now we can actually look at this as area under the curve. Okay, so that we have absolute value of x is equal to x if x is greater than or equal to 0 and negative x if x is less than 0. Now, let us consider the geometric representation of the absolute value of x. And we can see that the integral of the absolute value of x is actually the area under the curve. Okay, so of course, this is the graph of y is equal to the absolute value of x. Okay, this one, of course, is defined as y is equal y or f of x is equal to negative x, line leaning to the left, and this is y is equal to x. Okay, when x is greater than or equal to 0, y is equal to x. or f of x is equal to x, and when x is less than 0, y is equal to negative x. And we are going to consider -2 to +4. This is +4. So this is actually the area under the curve. Okay. Now, geometrically, we can actually find the area of these two triangles. Of course, we can easily find the area of the triangle. The area of the triangle is equal to 1/2 base times altitude. Okay, and if we will consider this as area 1 and this as area 2, then the total area is equal to area 1 plus area 2. Okay, now, if we will consider area 1, which is the area of the smaller triangle, okay, the area is equal to 1/2, the base is equal to 2 units. And of course, the height is equal to 2 since y is equal to -x. Hence, area 1 is equal to 2 square units. And area 2, considering the bigger triangle, bigger right triangle, is equal to 1/2 of its base. The base is equal to 4. The height is also equal to 4. Hence, this will give us area 2 is equal to 8 square units. Okay, hence, the total area, which is equal to area 1 plus area 2, is equal to 2 square units plus 8 square units, and this gives us 10 square units. Okay, so this will only show that geometrically, the definite integral is the area under the curve from A to B. So since we computed for the area of the absolute value of x from -2 to 4 geometrically, then the result of evaluating the integral of the absolute value of x from -2 to 4 must also be 10. Okay, it must be 10. Okay, so let us now try to evaluate the integral of the absolute value of x dx from the lower limit -2 to the upper limit 4. Okay, so since we have the absolute value of x defined as a piecewise function, x if x is greater than or equal to 0, and -x if x is less than 0, then c here will be equal to 0. And the integral of the absolute value of x from -2 to 4 is the integral from -2 to 0, okay? And when x is less than 0, f of x, the absolute value of x is -x. So we will have -x dx. Okay, then plus the integral when x is greater than 0, so it will be from 0 to the upper limit 4, 0 to 4. And when x is greater than or equal to 0, the absolute value of x is x. So we will evaluate the integral of x dx. Okay. Hence, this gives us integral of -x dx is -x squared over 2, and this must be evaluated from -2 to 0. Then plus the integral of x dx is, of course, x squared over 2 to be evaluated from 0 to 4. Okay, if we are going to evaluate the definite integral from -2 to 0 of -x squared over 2, okay, Then this gives us negative, okay? When x is equal to the upper limit 0, then we will have 0 squared divided by 2 minus the value of the indefinite integral negative x squared over 2 at the lower limit negative 2. So minus negative 2 raised to the second power divided by 2. Okay, then plus the value of x squared over 2 at the upper limit 4. So we will have 4 squared divided by 2 minus the value of x squared over 2 at the lower limit 0, which is 0. 0 over 2 is, of course, 0. Hence, we will have minus 0. Negative 2 squared is positive 4. Dividing it by 2 will give us 2. Minus minus is positive. So that will simply give us 2. Then plus 4 squared is 16. Dividing it by 2 will give us 8 minus 0. Hence, we will have 2 plus 8, which is equal to 10. Okay, so the integral of the absolute value of x dx from negative 2 to 4 is equal to 10, which is exactly the same as the geometric solution of the absolute value of x from negative 2 to 4 by considering the area under the curve y is equal to the absolute value of x. Let us consider another integrals involving absolute value. This time we will have f of x equals 1 absolute value of 1 minus x. Okay, but of course we have to define first the absolute value of 1 minus x. Okay, so here we have, let's other color. We will define the absolute value of 1 minus x. And by definition, this may be 1 minus x or the negative of 1 minus x. Negative of 1 minus x. Of course, the absolute value of 1 minus x is 1 minus x if 1 minus x is greater than or equal to 0. Of course, 1 minus x is greater than or equal to 0 may be written in the form 1 is greater than or equal to x, or x is less than or equal to 1. Or we may say x is less than or equal to 1. When 1 is greater than or equal to x, we may also say x is less than or equal to 1, reading from right to left. On the other hand, a negative of the quantity 1 minus x, the absolute value of 1 minus x is negative of 1 minus x if 1 minus x is less than 0. Now, when 1 minus x is less than 0, we can also say that 1 is less than x. Or we may say that x is greater than 1. Okay, so if we will go back to our problem, evaluating the integral of the absolute value of 1 minus x from negative 3 to positive 3, we can again use the property of definite integral, that the integral of f of x dx from a to b is equal to the integral of f of x dx from a to c plus the integral from c to b. And here, this time, we will consider c is equal to 1. Okay. We will consider x less than 1, okay, and x greater than 1. Therefore, this is equal to the integral from -3 to 1 plus the integral from 1 to +3. Okay, so if we will consider x less than or equal to 1, the absolute value of 1 minus x is 1 minus x. Okay, therefore, we will have the integral of 1 minus x times the differential of x from -3 to 1. This time, considering the integral from 1 to 3, hence we will consider values of x greater than 1. And when x is greater than 1, the absolute value of 1 minus x is negative of 1 minus x. So we have negative of 1 minus x times the differential of x. Okay, and evaluating the two integrals will give us integral of dx is x minus the integral of x dx is x squared over 2, and we will evaluate this from the lower limit -3 to the upper limit 1. Okay, then we can bring out rather -1, so plus times minus is minus. Okay, the integral of 1 dx, or simply the integral of the differential of x is x minus the integral of x dx is x squared over 2. Okay, and the indefinite integral will be evaluated from the lower limit 1 to the upper limit 3. Okay, therefore, this gives us, okay, the value of the indefinite integral at the upper limit 1. Okay, so we will have 1 minus 1 square is 1, so we will have 1/2 minus the value at the lower limit -3. Okay, when x is -3, then that gives us -3 minus when x is -3 square is 9. So we will have 9 over 2, okay, minus the value of the indefinite integral x minus x squared over 2 at the upper limit 3. So we will have 3 minus 3 squared is 9 over 2 minus the value of the lower limit 1. So that gives us 1 minus 1 squared is 1. 1/2. Okay. And if you are going to simplify this, we will have 1 minus minus is positive. So 1 plus 3 will give us 4. Then we have -1 minus minus will give us positive. So -1/2 plus 9 over 2 is 8 over 2, positive 8 over 2, and positive 8 over 2 is 4. Then minus, okay, of course, this will give us 3 minus minus 1 will give us 3 minus minus 1 rather is 2. And -9 over 2 minus minus 1/2 is 10 over 2, right? Okay, which is equal to 5. Okay, so this will give us 3 minus 1 is 2. Okay, and -9 over 3 Okay, sorry, negative 9 over 2 rather, plus 1 half is 8. Okay, so this must be, sorry, 8 over 2 is 4. Okay, so this must be positive 4. Okay, hence this will give us 8 minus minus 2 will give us 10. Okay, so 8 plus 2, which is equal to 10. So the integral of the absolute value of 1 minus x dx from minus 3 to 3 is positive 10. Okay, so this is how to evaluate the integral of the integral where the integrand is an absolute value. You have to express the absolute value as piecewise function and use the property of definite integral that the integral of f of x dx from a to b is equal to the integral of f of x dx from a to c plus the integral of f of x dx from c to b. Okay, let us consider evaluating another definite integral, integral of y squared times the square root of 1 plus y cubed times the differential of y to be evaluated from the lower limit 0 to the upper limit 2. Okay, of course, the definite integral can be evaluated by power formula of integration. So we need to express the radical as exponential or express the radical in exponential form so that we will have quantity 1 plus y cubed raised to 1 half, okay, times y squared times the differential of y. And if we will evaluate this by power formula, then we will let u is equal to 1 plus y raised to the third power. And the differential of u is 3y squared times the differential of y. But we have y squared dy here. Hence, du over 3 is equal to y squared dy. Okay, we have correction factor 1 half. So evaluating the integral by power formula with a correction factor 1 half, okay, then we will have 1 plus y raised to the third power u raised to n plus 1. We have n is equal to 1 half, so 1 half plus 1 is 3 over 2. Divide it by 3 over 2. And we are going to evaluate this from the lower limit 0 to the upper limit 2. But before we evaluate the indefinite integral within the limits of integration, let us simplify first. Now, of course, we can do cancellation here. We can cancel 2 so that we will have the factor 1/3, and we can write 1/3 before the grouping symbol. So we can factor out 1/3, okay, times the value of the indefinite integral 1 plus y cubed raised to 3 over 2, okay, from the lower limit 0 to the upper limit 2. So this gives us 1/3 times, when y is equal to 2, okay, then we will have 1 plus 2 raised to the third power is a, okay, raised to 3 over 2 minus the value of the indefinite integral at the lower limit 0. So that gives us 1 plus 0 raised to 3 over 2. Okay, hence we will have 1/3 times 1 plus 8 is 9. Square root of 9 is 3. And 3 raised to the third power is 27 minus. Of course, 1 plus 0 is 1. The square root of 1 is 1. And 1 raised to the third power is 1. Okay, therefore, the indefinite integral is equal to 1/3 of 27 is 9. Oh, sorry, 27 minus, wait, minus. Okay, so this will give us 1/3. 27 minus 1 is 26. Hence, the definite integral of y squared times the square root of 1 plus y cubed dy, evaluated from 0 to 2, is 26/3. Okay, this time we will consider evaluating the integral of sine of x dx from negative pi to pi. Okay, and this is equal to 0. Okay, why is it equal to 0? The integral of sine of x dx from negative pi to pi is equal to 0 since sine of x is an odd function. Okay, recall that in trigonometry, we have learned that sine of negative x is equal to negative sine of x. Okay, and based on the definition of odd function, if, okay, definition is if f of x is equal to negative f of x, then the given function is an odd function in x. And recall that there is a theorem in even an odd function that the integral of f of x dx from negative a to positive a is equal to 0 if f of x is odd. Okay, and since sine of x is an odd function, then the integral is equal to 0. Now, on the other hand, if we are going to evaluate the integral of sine of cosine of x dx from negative pi over negative pi to positive pi, then we can consider the theorem on integrals, indefinite integrals, that the integral of f of x dx from negative a to a is twice the integral of f of x dx. Okay, so you can always use the theorem when f of x is either odd or even. Okay, so let me write the other theorem. The integral of f of x dx from negative a to a is equal to twice the integral of f of x dx from 0 to a. That is, if f of x is even. Here. Okay. Let's see. Now, if you want to verify that the integral sine of x dx from negative pi to pi is really equal to 0, then we can actually do that by applying the definition of definite integral. So let us try to evaluate the integral of sine of x dx from negative pi to pi. Okay. Of course, the integral of sine of x dx is negative cosine of x. And this must be evaluated from the lower limit negative pi to the upper limit pi. Okay, let us just bring out the negative sign. for easy facilitation of the computation. So minus, okay, cosine of x when x is the upper limit pi is cosine of pi minus cosine of x at the lower limit negative pi is cosine of negative pi. Okay, which will give us minus, okay, cosine of pi is cosine of 180 degrees and cosine of 180 degrees is negative 1 minus, okay, cosine of negative pi is cosine of negative 180 degrees, which is also negative 1. Okay, and simplifying gives us minus negative 1 minus minus is positive. Okay, of course, negative 1 plus 1 is 0. Therefore, the integral is equal to 0. So it only shows that the integral of sine of x dx is really 0, even if we consider this property of definite integral when the integrand is odd, or we can evaluate it using the definition. It will give us the same result. Okay, so here we consider sine to the fifth of x dx from 0 to pi over 2, which can be evaluated by Wallis formula. Okay, since the exponent of sine is 5, we are going to start with 4 in the numerator. So subtracting 2 at a time, we have 4 times 2 divided by 5 times 3 times 1. And alpha is equal to 1 since the exponent is 5. Okay, therefore, the integral is 4 times 2 is 8, 5 times 3 times 1 is 15. Okay, now this time, if we will consider evaluating sine to the 10th of 3x dx from 0 to pi over 6, it seems that we cannot apply Wallis formula in evaluating the given integral since the upper limit is pi over 6. In Wallis formula, the lower limit must be 0 and the upper limit is pi over 2. Okay, but since here the upper limit is pi over 6, okay, it seems that Wallis formula is not feasible to use, but we can actually change the limits corresponding to the change in variable. Now, we can change the variable by introducing a new variable, say theta, replacing 3x. If we will do that, then if we will let theta is equal to 3x, getting the differential of both sides will give us d theta is equal to 3 times the differential of x. But we will have a correction factor 1/3, of course, since d theta over 3 is equal to the differential of x. And corresponding to the change in variable, we need to change the limits of integration. Okay, let me write it here first. No? Okay, so corresponding to the change in variable, then the new integrand is now sine to the 10th of theta, okay, with a new variable of integration, theta. And we have the correction factor 1/3. Okay, now corresponding to the change in variable is the change of limits. Okay, hence, if we will consider theta is equal to 3x, when x is equal to the lower limit 0, okay, so when x is equal to the lower limit 0, then the new lower limit, okay, when the variable of integration is theta is 3 times 0, which is equal to 0. So the new limit of lower limit of integration is 0. And when x is equal to the upper limit pi over 6, then the upper limit of integration theta is 3 times pi over 6. And note that 3 times pi over 6 is pi over 2. So the new upper limit is pi over 2. And look at the result after changing the variable to theta. The new variable of integration is theta, sine to the 10th of theta d theta. Okay, and corresponding to the change of variable is the change of limit from 0 to 0, pi over 6 to pi over 2. And the new integral can now be evaluated by applying Wallis formula, since the lower limit is 0 and the upper limit is pi over 2. So applying Wallis formula, this will give us 1/3. 1/3 is the correction factor. The exponent of sine of theta is 10. So subtracting 1 will give us 9. So we are going to start with 9 in the numerator, subtracting 2 at a time. So 9 times 7 times 5 times 3 times 1. Okay, divided by, okay, we have 10 times 8 times 6 times 4 times 2. And then multiply by alpha. Now, since the exponent is even, 10 is even, then alpha is equal to pi over 2. And let us just do cancellation. If we will do cancellation, okay, 3 and 9, this will give us 3. Okay, what else? We have 5 and 10, this will give us 2. Then we have 3 and 6. You can cancel 3. Okay, 6 here will give us 2. Okay, therefore, multiplying the factors in the numerator, we have 7 times 3 is 21 times 5 is 21 pi. Okay, over 2 times 8 is 16, 32. Okay, 64, 128, 128 times 4 is 500, 512, right? Okay. Right? Okay, 2 times 2 times 2 is 8. This is also 8. So 8 times 8 is 64. 64 times 8 is 500. Okay. Therefore, the integral of sine to the 10th of 3x dx from 0 to pi over 6 is 21 pi over 512. Okay. Now, you can actually always consider changing variables, no, when evaluating integral of powers of sine or cosine. But you have to consider, if you will use Wallis formula, you have to consider that the lower limit is 0 and the upper limit is pi over 2. Now, in case that the upper limit is not pi over 2, you can always look at the argument, okay? Like here, the argument is 3x and the upper limit is pi over 6. Okay, the denominator of the lower limit must be twice the numerical coefficient of the argument. If it is so, it will always end up to pi over 2 after changing the limits corresponding to the change of variable. Okay, so you can see here that 6 is twice 3x. Okay, so that's it. So these are examples on definite integral.